All right, so I'm Paul Wessel. This is my brainchild, although I didn't do this alone, obviously. There's a team with me and behind me. We have a core team of 4 people, these handsome gentlemen. This is from a summit we had, a developer summit out in Hawaii in February. Consists of Remco Charoux, which is independent consultant. He consults for NOAA. We have yours truly here in Hawaii. Walter Smith, who I co-founded GMT with back in the day. We'll talk about that. He's at NOAA, the Laboratory for Satellite Altimetry. And then we have Joaquim Luis from the University of Algarve in Portugal. So this is the 4 horsemen of the apocalypse, I guess, who is sort of in charge of the GMT day-to-day work. In addition, we couldn't get any of this done if we hadn't had generous support from many organizations and institutions, funding from NOAA, NSF, cost sharing from NOAA and Soest, and startup packages. A lot of places around the world has contributed time and equipment for web servers, FTP mirrors, and that sort of thing for decades. So we're very grateful for this. And then there's tons of people who have contributed smaller changes and packages over the years. They come and go. This is just some. It's lost in the history of time, some of them. So before we get too far, we'll just talk a bit about what GMT is. And of course, it stands for the generic mapping tools, although really early on it stood for gravity magnetics topography, because that's what we were doing for our thesis. And then we realized that, hey, if you plot x versus y, it doesn't have to be gravity versus distance. It could be other things. So we changed the name. It was officially released in 1991, October 8th, which means that tomorrow is the 20th anniversary, and there will be cake at that time. We were one day early. We couldn't really do this on Saturday. GMT is a suite of tools, basically C programs written in PostScript that are command line. And because of this, it installs and runs under pretty much any operating system. This operating system has come and gone during the last 20 years, but it compiles on anything. We have a lot of experience in configuring things for different operating systems. We've been fortunate to have continuous NSF support since 1993, and currently going with a grant to 2015. We've never had a grant turned down. We even had a person who only got the other page of our proposal and still said, recommend funding. So that's a pretty good track record. GMT started back in the dark and dreary days in the 1980s when I was a grad student at Lamont. And Walter and I were trying to do global geophysics, and it was extremely frustrating because the software was written a decade before in the 70s and all expected to read punch card formats. Although the punch cards were gone, the file formats were propagated further, and it was very difficult to read your own data and make changes. So after a while, we realized we just have to start from scratch and write our own code. So that's why we did it. And I found, I did some archaeology and found that the earliest timestamps of some of these codes are from 1987. So in 87, we started writing this. In 88, we released a version 1 at Lamont. We had a little presentation. We talked about why we did this and what it was about. I found the original copy upstairs. And this is pre-internet, but some people like Fernando got a job here, and he took GMT with him on a tape or a cartridge or something. So it sort of spread very slowly to different places before the initial release in 91. GMT was strongly shaped by the trends of the 80s. This meant we were quitting using mini VAXs and workstations like Solaris Sun OS boxes came along. So we started to develop software that fit that new environment, particularly Unix. And we wrote things in C, and PostScript had just been released. PostScript printers were just coming to revolutionize desktop publishing, and we wanted to figure out how can we write plotting that will actually work on these new laser writers instead of the Versatex and whatever we had back in the day. So the design philosophy for GMT pretty much follows the Unix philosophy, where you try to design very small tools, modules, that are focused on a specific task. And they can do that well. And that means it's a limited amount of things to think about when you're looking at that module. There's very few things that can go wrong. To do something more complicated, you'll then put these modules together in various ways to achieve more complicated results. GMT tools integrate easily with other Unix tools because they are kind of Unix tools themselves. And what that means is that They tend to read their data from standard input and write their results standard output. And you can then redirect these directions where the data is coming from or going and build a very complicated system. I mentioned it's written in PostXC. It's very portable, and it's easy to maintain and extend to new platforms. It is a command line interface, so you're typing things in the command line window, but there are people who have added GUI front ends where you click on buttons and so on. We will never write a GMT GUI because it's a huge trade-off between what is simple for the user and what you can accomplish. So we want to have a simple command line interface that lets you do all kinds of things. In some situation, if you just want to achieve a limited result, you can slap a GUI on top and just do those things. But people are doing this. There's iGMT, there's Miron, there are web portals that let you build maps online. So why is GMT popular? Because it's quite popular. The price is right. We don't charge for this. So you can download it for free from servers around the world. We have FTP servers on all continents except Antarctica. It's open source code, so you can look at it, you can make changes, you can use it for your own purposes, just as long as you give it away freely if anyone asks. It's easy to install and runs on all major platforms, so all the Unix types and also Windows. That covers pretty much everything that's of interest. It has a relatively low technical threshold. And what I mean by that is it's not too hard to learn. It's a little steep learning curve, but once you get up there, it's not too hard. And it relies on very basic libraries that are available on pretty much all platforms. We decided early on to use architecture-independent open file formats, which turned out to be a good idea because that means it's easy to exchange data. It's easy to collaborate with people with different machinery and different operating systems because the files port very easily across. So NetCDF, which was released in the early 90s, we switched to that pretty quickly. ASCII, of course, is always handy. And other formats we can exchange through the GDAL system, which I'll talk a little bit more later. Other things, as I mentioned, the PostScript revolution in the early 80s, we always aim to produce very beautiful PostScript output. But that's usually no longer the end station. We tend to convert that to something more processed, like PDFs, because it greatly reduces the size of the files while still being a vector graphic format. Or we convert it to raster images like JPEGs or TIFFs or PNGs or whatnot for use on web pages or for talks or something. GMT is very flexible and extensible. That means that if you have a particular problem, you can model your code on GMT. You can borrow bits and pieces and write a new code that is specific to your discipline, perhaps. And that's how some of the GMT supplements have arisen. People have written code following GMT, so it plays with GMT well, but it does something specific to a certain discipline. You can share that with us. We might incorporate it in our supplemental package, and a lot of people benefit. Also, the developers, as I mentioned, they're also scientists and users of GMT. And the benefit of that is that when we add new features, they're added for a reason. They want to do something real that's important. It's not just added for a gimmick like commercial software. Because you've all been there. You just spend X $100 on software, and then the new version comes out for a $99 upgrade where they fix all the bugs in the previous version, and they add some useless options that you don't need. Right? You don't do that in GMT because there's no money to be made. GMT interfaces with other tools. We'll see examples of this, particularly MATLAB, GISs, Google Earth, Miron. As for platform support, I'll repeat a little bit this. With Unix type workstations, there's sort of three flavors, and it sort of follows the historical trend. When we first started with GMT, we all used Sun OS boxes, Solaris. And at the time, there was many Unix players. HP had their own Unix. SGI had their own Unix. IBM had their own Unix. These things slowly got left behind, and people moved to Linux in the middle 90s, early 90s. And people are still using Linux quite a bit. But also in the late 90s, early 2000s, Mac OS came on board. And a lot of people who used Linux have moved to that because that also allows them to do desktop publishing, Microsoft Office, Adobe products, and so on. So during this time, I've seen lots of people who used to have Linux boxes and Windows PCs to do their science combine that into a Mac platform because of their need to use tools like GMT. But that doesn't mean you can't use Windows. In fact, most people still use Windows, even in science. And you have several options. You can install both Windows and Linux on the same machine and do a dual boot. And then you get a real Linux workstation. You can install services for Unix or subsystem for Unix applications that has been renamed, or Sigwin under Windows that lets you open up a Unix shell and you can install GMT and run things there. You can run virtual Linux machines through VMware or Virtual Linux, or you can actually run GMT as in a DOS command window. It just doesn't let you do a lot of fancy things like scripting, but it works. So who are the people that are using GMT? Well, I don't know exactly who they are, but we know sort of where they are. So Google tells us that we're seeing about 20,000 website hits per month. It sort of scales with where the populations are. We get hits from almost every country except Greenland, which is not really a country, and places in Africa, and that Uzbekistan or somewhere up there. I'm not quite sure. So we see a lot of hits on the website. As far as downloading the code, we see over 2,000 individual FTP downloads per month. About a third seems to be Windows. And it's a little tricky to figure out. Depends, because we offer both 32 and 64-bit Windows installers, and some people get both. So, but based on the browser statistics, it seems like Windows is about a third, Macs are about 1/5, and the rest are Linux, Solaris, other things. Maybe, something like that. That's our best guess. So GMT has been called the Swiss Army knife of mapping tools. It's a little bit frightening. This is sort of symbolic of the learning curve in the beginning. There's a lot of new options, ways to go wrong. So it combines a wide array of tools, all these things you can pull out and does something different than the other one. You can configure these in various ways by scripting. And by scripting, I mean you write commands and you glue your commands together with, let's say, a shell script or a Perl script or a Python script or something like that. As I said, it's possible to cut your fingers if you're not careful in the beginning until you get your hands around this tool. One thing that we strive for in GMT is to try to help to share scientific knowledge. And I think it's pretty obvious that you can share your science much quicker if the software you use are freely available or cheap. Because we might be relatively wealthy here, but that's not true in many places around the world. So if you can keep costs down or zero, you can let other people participate in the science enterprise without having lots of funds. Data sets should be available in well-documented non-proprietary formats. This really helps when you're trying to share. We've all been struggling with strange formats, undocumented. Turns out you need a commercial product to open it. Publications should contain everything needed to reproduce and extend results. I would say we're making progress on all these things. The last one even with publishing supplementals and data sets online. But typically you can't actually reproduce someone's work because there is software involved, there's special codes. But we're getting toward a point where people can reproduce published results quickly and then extend it. So GMT was designed with this in mind and continues to be evolving with those goals in mind. All right, so what can GMT actually do? Well, there's several blocks of tasks. One is data processing and data manipulation. And this, we'll see more details on this, but for some purposes, we actually source out tasks to the operating system, such as sorting files or doing basic text processing, like decimating a data table or pulling out subsets of files. Those things we haven't replicated in GMT code because good tools exist that are general purpose and available. And then we combine these tools with scripting to build our workflow. Another large chunk of GMT is concerned in making plots of various sorts, and that is all through PostScript. GMT only produces PostScript as the first plot format out. And this can range from tiny little stamp-sized things to wall-sized posters. You've seen around the building a lot of wall maps like this one there or bigger one upstairs. PostScript is device independent. It doesn't care if you have a 10 by 10 meter plot. You just have to have some way to realize it in the end on a plotter. Typically, we convert the PostScript to PDF or raster images because that is an easier way to handle these large plots. PostScript is a programming language. So it has a lot of overhead and a lot of extra fluff to generate these figures. PDF strips out all the programming language aspects and focuses on the graphics. So that's why you see this dramatic compression from a gigabyte PostScript file down to a few tens of megabytes for a PDF. So it's a good way to keep things compact. And then recently we started to branch out to make KML plot generators that we can use with things like Google Earth. We can plot vector data, points, lines, and polygons as overlays for Google Earth. We can also convert GMT images into geotiffs or PNGs, and we also build simple KML wrappers that let you load these things into tools that understands KML. Now, GMT is not a GIS or an image processing package. There's a lot of overlap between what we do and these kind of packages. But we work with such packages for some aspects that we aren't really covering ourselves. For the data processing and manipulation tasks, there's a whole bunch of things. We're filtering time series. That's one thing. Filtering 2D data, grids, with various spatial filters or frequency filters. Fitting low-order models to grids. It can be Fourier trends or polynomials. Gridding data is a big thing. A lot of gridding routines in GMT. Resampling data. It can be resampling grids or data set at different locations. Arbitrary mathematical operations on grids and tables. Cut and paste grids and get things out of, get subsets out. Blending grids that might overlap to create a unified product. Directional derivatives needed for shading of images. Grid masking to highlight areas of the data or exclude areas of data. Project data between different coordinate systems and datums. Triangulations, Delaunay and Voronoi organization of spatial data. Spectral estimation, Fourier transforms, that sort of thing. Reformatting data to work with other packages. Some geospatial operations, subsets, and extract subsets, sometimes based on these various operators. I mentioned supplements earlier. These are things that cover tasks that we don't consider generic. So generic means it should apply to anybody in science. There's nothing there about gravity or earthquakes or oceanography. Just general stuff. But things that are a little bit beyond the general stuff, getting into disciplines, we have supplements. There's one that deals with plotting focal mechanisms and GPS velocity fields and errors. There's one that deals with the specific Mercator grids that Samuel Smith makes from satellite altimetry, be it gravity or predictive bathymetry. Plate tectonic applications, backtracking reconstructions of data back in time. Analyzing and plotting marine geophysical data records from NGDC. Crossover analysis, you have ship tracks or other tracks that intersect, and you want to adjust them to minimize the mismatches like this at intersections. And spherical gridding, gridding on a sphere, it behaves a little bit differently than Cartesian flat Earth. As I mentioned, GMT uses PostScript. PostScript is a programming language. It has a lot of knobs at the low level to affect your plot. And we want to get access to some of those things because that's where some of the beauty in plots can be enhanced. We can obviously plot points and lines and polygons. Text and labels and legends can be placed on maps in various forms. These are just quick examples. We can do histograms of various types. Base maps, coastline, rivers, borders, that sort of thing, using the global sea level, I can't remember, shore, hierarchical, high-resolution shoreline. That's a complicated one. Contour maps of various types, and color images from grid data or raw data turned into grids, perhaps. Perspective view, 2.5D. We stop at 2.5D, meaning this unique x, y value with each z value, because the way we developed GMT, we were doing science that didn't deal with volumes. So I'm not a fluid mechanics person. I don't do 3D volumes. And that is reflected in our tools. We don't have a tool to do 3D rendering in volumes. Also partly because PostScript is not a good tool for that, because PostScript doesn't know anything about transparency, which is kind of crucial when you try to look into volumes. So there's two reasons why we don't do 3D rendering. And vector fields and wiggles along tracks. So the details of the graphics I was alluding to can be addressed with PostScript attributes. And we have full control over what lines should look like, whether they be dashed or dotted or some shape, and and what happens at the end of lines. And when lines change directions, what happened at the bevel point. These things you can tinker with and set through GMT defaults to achieve a very beautiful final result. For lines, we plot lines obviously, but we also have things like fronts and faults and labeled lines that are very useful in science. And you can configure these things any way you want. Symbols and polygons and so off can be, and texts can be plotted in color, of course, but you can also use patterns. Some of them can be geological map kind of pattern, or images. These can be just some JPEG. So you can make your own pattern to make things unique. And you can plot various symbols, the standard basic geometric ones, or you can design your own symbol and then use that as a symbol to plot your data globally. KML Plot Generation. As I mentioned, it's just simply two forms of output right now. This can possibly extend in the future, but we're doing overlays that are vector overlays for points, lines, and polygons. Some of these can have legends and labels with them. And then you make the wrapper from PNG images that basically start with a GMT plot, let's say a map of gravity that gets turned into a geotiff or a PNG and then loaded into one of these tools that can read KML. And because Google Earth is the 800-pound gorilla in that context, and that's like 364 kilo for those who prefer SI. Okay, I'm just going to go through some GMT graphics examples. Some of these you've seen before, some you may not have seen. And a typical thing is going to be contour maps, color maps and images and combinations of all these, Google Earth overlays, and some animations. So for gridding, for instance, we make contour maps and color maps from that. There's several kinds of griddings that are allowable in GMT. There's triangulation, which is the rawest form of gridding. You can directly contour data by considering any 3 points triplets being a part of a plane. We can image that directly, like in the upper left here, and we can grid the data and create a grid based on these planar facets. There's a nearest neighbor gridding algorithm in GMT. There's also surface splines, either minimum curvature or some sort of tension. And we also have gridding with Green's functions that goes from 1 to 3D Cartesian up to spherical gridding. What's Alexander the Great doing here? Well, we find that although GMT is used widely in the Earth and ocean and sometimes space sciences, it's also used by all kinds of people. We get email from these people, and they show us these things. And this is a person who's working on historical maps of Alexander the Great's empire. And this is a GMT map where there's a combination of spatially dependent topography shading, highlighting his empire. And then there's custom data of where these things happened, custom symbols that identify battle scenes and so on. And this is all then generated with GMT. This is from the Wikipedia GMT page, which is something we don't maintain at all. You can easily, this is one of my figures, you can easily mix data, which is the top here, obviously. And the cutoff, we can draw XYZ lines. You can just plot models and sort of trying to show what the flexural deformation beneath the Hawaiian Ridge might look like. There might be some underplating based on the seismic data. And then there's the elusive hotspot stem coming up and feeding us, feeding little islands. Tsunami travel times. This is a very basic GMT plot where we combine color from one data set, travel times, shading from another data set, the bathymetry, and then superimposed coastlines, great circle distances, annotations, symbols, that sort of thing. Very standard GMT plot. All roads lead to Rome, but it goes a lot faster if you can go great circle. So this shows distances to Rome in kilometers throughout the world with a few selected locations, great circle there, and the distance and sampling. So this script that created this is 5, 6 lines. It'll do all these calculations and determine all these numbers and place all these legends. Pretty simple, actually. Data exploration and imaging. So if you're doing exploratory data analysis with grids, you might make just a basic color image of your grid. The colors indicate elevation. You can clearly see there's variability in elevation here. This is somewhere in the Rockies near Denver. But it's kind of dull. There's no sense of slope. Slope's not really being portrayed. By doing a calculation of directional derivatives, we can combine a shading map with the colors and then dramatically bring out the more subtle variations. Because the derivative, the directional derivative, highlights short wavelength information. It brings out the shorter wavelengths in the image, such as rapidly changing slopes. Because the shading grid is a separate grid from the topographer grid that we use for color, we can manipulate it further. We can scale up the amplitude, we can blur it, we can filter it, we can enhance it, we can take out some ambient light to make it darker till you get the result you want, or we can boost the intensity way up, which tends to bring out really the structure of the data and maybe some artifacts here and there that you wouldn't have noticed otherwise by just looking at, way out of range saturation for the shading. Or we can combine different other elements in here. We have the shading produced by a very large spaceship sitting over the Rockies, like in Independence Day. And the colors don't have to come from the elevation. Here, the colors come from the strike of the data. And that lets you see variability in how the morphology changes, where the riverbeds are, and also where things are planar or changing rapidly. And you can combine all these, of course. The Antipode Distribution. This came out from a GMT workshop challenge. We want to know, if you're standing some point like here, and you go straight down through the Earth's center to the other side to the antipode, is the land there also? It turns out there are only 4% of the Earth's surface that has a terrestrial antipode. And Hawaii is one of them. You can see Hawaii fits into the back mapping of Africa, Southern Africa. So we're lucky, I guess. I'm not sure. But most is mixed. And the red area shows you where the terrestrial antipodes are located. Odd plot, but can be done. The poles of inaccessibility. Okay, this is a geospatial calculation in GMT where we look at the distance from the nearest coastline. And when you do this, you get lots of local maxima, but you also get two global maxima. One is being called Point Nemo, which is the point in the ocean that is furthest away from all land. It's a particularly bad point to fall off the boat because you have a very long swim. I would recommend Easter Island, but it's quite a bit. And these two gentlemen are the ones that have been closest to that point. No one's actually been to Point Nemo, but John Moody and Left and Denny Hayes came within about 100 kilometers of this point back in the 70s. Since we aren't collecting data in the Southern Ocean anymore, no one has been back there apparently since 72. On land, there's a corresponding point. It's called the center of the Earth, and it's as far away from ocean as you can get. So if you have issues with sharks and drowning and you don't like those things, I recommend buying some real estate in northern China. They say it's nice. John Moody. Google Earth. This is a screenshot that Nathan Becker from PTWC provided me. It shows a GMT plot of the energy, the kinetic energy of the wave from caused by the Japan earthquake, superimposed with the travel time contours. So this allows PTWC to look at the data in different angles and share with city and state civil defense, and also with the media, I suppose, to explain what is happening and how things are spreading out. This was the cover of Science magazine in 2009. This is Cecily Wolf's work on tomography and the Hawaiian plume. The front piece, though, was something that Dave Samble and I put together by taking the Samble-Smith predictive bathymetry and plotting it in GMT tiles and making it into KML files so that you can put it into Google Earth and adjust the viewing position. Because in Google Earth, you can clamp an image to sit on the sea floor. You get basically a 3D effect. So that's how that image was generated. Making GMT movies. Okay, well, movies is pretty simple things. We all know what movies are. They're a bunch of photos or plots displayed in rapid succession in some orderly fashion, and it generates motion. So to do this in GMT, we just simply have to have a script that creates a plot, presumably that changes with time, and then these individual plot PostScript files are saved. We make a certain dimension of the plot. We then convert these frames to TIFF or PNG or some other raster with PS to raster, which is our front end to GoScript, which turns PostScript into other formats. And these frames can then be put together to make an animated GIF, which very good if it's a relatively short video. Or you can make an MPEG or MP4 movie or create a DVD if you like. It's your choice how ambitious you are. Now, because these frames typically are independent, that is, plot 50 doesn't really depend on plot 49. You can run the two plots at the same time if you have enough computers or enough CPUs. So it's very well suited to multiple machines and multiple cores. So the movies I'm going to show you, they're all done, spreading out on all the CPUs that I have, and they go pretty quickly. So we're going to look at 3 examples of movies. One is just simply repeating that exploratory data analysis with the topography. But this time we're making a movie that changes the viewing angle for the illumination. And as the illumination spins around, you'll see different aspects of the topography being highlighted. Because when the illumination is 90 degrees to some feature, that's when you see the largest effect. And this lets you explore your data. Look for trends, look for artifacts, so forth. It's not too hard to write a script like this, just looping over azimuth and make the same plot again and again and again. So the trends will stand out for different angles, and you'll see the errors in the data, which you may go back and reprocess perhaps, and then move forward. Okay, the old spinning globe. Spinning globes are easy and boring. They're easy to make in GMT. It's very straightforward. It's just a plot, and you just change the viewing point and make another plot, change the viewing plot. So it's quick. It's one of those 2 that I started off with. We're going to look at the more detail. It took me about between an hour and 2 hours to just set it up the first time. And once I set it up, it's pretty simple. I'm plotting Dietmar Müller's age grid on the surface of the Earth, but I'm using the shading from the underlying bathymetry, and then I plot topography over land. So it shows several data sets at the same time. And that's it. I didn't plot seismicity. I didn't plot plate boundaries, but you could have overlaid all those things and other data on top, or legends and whatnot. But this was just a quick and dirty job to show how it is. And then I made 720 high-def frames that I rendered at 30 frames per second. So that's every half degree of longitude changing the viewpoint going around. So that's the only thing that changes, the central longitude of the plot. Then I am messing around, simulating the real sun shining on the Earth, and part of it should be dark, part should be light. That's done with GRE math, which will take the shading that I computed from topography based on the slopes, and then superimpose the effect of facing away from the sun, facing towards the sun. So this is the same movie that I started off with on the title slide, but it's a larger version. So there's some planets in the background there. So you can see as this goes around, you can see the mid-ocean ridge system in red. That's the youngest seafloor. The blue is the oldest. We have the old patch in the Western Pacific. You see the spreading system in the Indian Ocean, going through between Africa and Antarctica and up to the mid-ocean ridge. And this movie will repeat, and will go around and around and around until we get tired of it. But it's useful to illustrate plate tectonics on the global scale as a globe. Okay, a little bit more ambitious undertaking is a flyover of this ridge system that we just saw. This took me about a full day of work to get right. So since I'm probably fairly experienced with GMT, it will take most people a little longer maybe, but not that much longer, all right? No, not decades. Some of these examples will be part of the GMT distribution as examples for animation. Because once you have an example to follow, it's very simple to modify things. So this script made over 5,000 HD resolution frames, again, at 30 per second playback. As I said, this is really well suited for multiple machines and cores. You just split all the jobs into as many machines as you have, and you can cut down the time. It's like stupid parallel. That's how simple it is. So this makes a 3-minute movie. It took a couple of hours to run on my old Mac. It has 8 cores, so basically it split the job into 8 chunks and run them simultaneously. You'll see this was very simple. We can improve this further. The flight path is a little bit simplified. We will see that we're going to follow this mid-ocean ridge system at, I think it's an elevation of 800 kilometers. And when we turn, we just turn like this. We don't bank. So I didn't have time to make it really slick. And eventually, we hope to add true 3D effects where you can actually fly down and through bathymetry topography, kind of like Fledermaus does, but for free. All right, so we're going to trace the 55,000 kilometers of mid-ocean ridge system. I simply took someone's file of the mid-ocean ridge and filtered it based on some points, and that's my flight path. We're going to start over here in Russia, where the plate boundary goes on land, gets diffuse, and we're going to fly, I guess that's west and then south through the Atlantic and end up over at the Juan de Fuca plate, where the spreading system enters under Canada. So this movie is rendered at 1024 by 768, which is the resolution of this device up there. So that's the limiting factor. I also done this at full 1920, whatever that the HD is, to look at my home screen TV, but I can't do it here, so we're a little limited. So we start off in Russia, and we're going down the Gackle Ridge. It's the North Pole right there in the corner. And we're, oh, this is getting a little sickening. We're turning down the ridge system. Whoa, Kolbansky Ridge. Getting into Iceland, down the Reykjanes Ridge. We see the seismicity as the red dots. It's the Charles Gibbs fracture zone, I believe. Getting down to the North Atlantic. There's the Azores Triple Junction. We're going further south in the Northern Atlantic, getting closer. We see all the fracture zones, really short offset fracture zones everywhere with seismicity. Now we're turning down through the equatorial Atlantic. We're going to pretty soon get to the large offset fracture zones, the Romanche fracture zone. You see Africa in the upper left corner there. There's the large fracture zone I mentioned. We're turning south in the South Atlantic. You see the St. Helena seamount chain up there. Otherwise, very few seamounts in the South Atlantic. Something on the left on the African plate, that's the Valvis Ridge chain. Getting to the south of the South Atlantic, we're turning over the Bouvet Triple Junction and facing the Indian Ocean. Spreading is pretty slow down here. You can see the changes in the fracture zone, evidence of change in plate motion over the last 50, 70 million years. We're getting in between Africa and Antarctica here, Andrew Bain fracture zone. There was a reunion up there, getting into the Indian Ocean Triple Junction, Rodriguez Triple Junction. Whoa, hold on, turning right, getting into the southern oceans between Australia and Antarctica. Things look smoother because there's less data. You can see the ship tracks where there is data. Seismicity still on the transform faults, getting into the AAD discordance zone. Beautiful propagators coming off there. Large offset fracture zones again, the Balleny. There was a quake over magnitude 8 a few years ago on the fracture zone down here. A lot of deformation. It's the southern end of the Pacific, a lot of extension, and then we go up the Pacific Antarctic Ridge. You see there's no clear actual high, but suddenly it starts to appear. There's Hollister Ridge, the enigmatic volcanic ridge, the Eltanin fracture zone system, and now we're up on the Pacific Antarctic Ridge, very clear axial high. There's the foundation seamount chain, the microplate area. Here's Easter microplate, seismicity following all the way around. There's the, I can't remember what that's called. It goes too fast. Sojourn Ridge, various fracture zones. We're getting up to the Galapagos Triple Junction right there. Galapagos was off the ridge right now, off the plot. The Clipperton and Sequoias fracture zones, getting into the Rivera fracture zone, Middle America Trench. Now the plate boundary is getting on land, going through the Gulf of California, and the spreading ridge becomes a transform fault to San Andreas, causing a lot of seismicity. They get off again the ocean at Mendocino, following up the Juan de Fuca Ridge all the way up, and then bang, we slam into the continent. And that's 3 minutes and 5,400 slides. So, GMT releases. I mentioned we did this, started way back, version 1 in '88, and there's been many releases since then. Tens and tens of versions. The last one that most of you are using is 4.5.7, which we released in the summer. But after that, we started with GMT 5, which is all still a beta version release. So GMT 5. What is GMT 5? Well, what's new in it? Well, it's actually a big, big rewrite under the hood, which means that most of the users won't really notice how big this rewrite was because they tend to use the tools and not dig into the code. But there are many new tools, and there's more options and a lot of streamlining that you will benefit from. For developers, meaning people who might want to write their own code using GMT, there's a huge change. You can now have an API access to GMT functionality. and I'll talk about what that means. New features for users. We have much better interoperability with GIS systems, ARC info through the GDAL system. Basically, you can now import and export what we call OGR GMT files. And what these things are, you can think of it as an ASCII shapefile. We have developed a new format. This was suggested by Brent Wood at NIWA in New Zealand, and I helped him with that, and it was implemented by Frank Warmerdam, which is the man behind GDAL and now works for Google. So it's basically taking what metadata you find in a shapefile and converting it to an ASCII file that GMT can read and parse. And the beauty is that older versions of GMT can also read these files. They just simply ignore the metadata, so it just reads the spatial stuff. We also have built in a bridge with GDAL to read rasters and grids. That means that GMT5 can read any grid format that GDAL supports, which is very wide, and also read images such as geotiffs directly into GMT without going through some conversion. We've started to build in multi-core support in some tools. Now, for a lot of GMT jobs, you can do the dumb parallel, as I said. You just write several scripts and you start them at the same time on your computer that has multiple cores, and they can run at the same time. And that's the best way to use multiple cores. But some tasks, like filtering, is very slow, but it cannot be sped up if you can partition the code to run simultaneously. So we started to add such support by using OpenMP, which is available built in through the GNU CC compiler. We just started doing this, and we're going to expand it to many of the tools that can benefit from it. We have greatly improved the consistency of GMT for table I/O. We now use a unified library that reads. So all the programs uses the same library. It locates all the bugs in one place, makes it easy for us to maintain, and it gives the same performance everywhere across the platform. There's some new options that get a little nitty-gritty here, lowercase -o and -I, to allow you to select which columns of your big table do you want to be plotted. Typically, before, you would use something like cut and awk or some other tool to pull out and rearrange things, and maybe scale column 9 by 10 to make it the right unit. That's now built in at the low level into a GMT global option. And this also works with binary files and .cdf files. So you can do this thing that you couldn't use awk for in the first place. And even if you have native binary files, you can now mix the data type per record. So instead of having a record that is all double precision or all single precision, it could be a mix of integers and floats and swapped doubles. We can handle that. And you can also read .cdf track files, XY files directly. You can't write them, though, but you can read them. There's several new tools and many new options that are available. We have added PDF transparency. I mentioned earlier that PostScript knows nothing about transparency. There is no such thing, so it's very difficult to implement, right? It's not there. But Adobe has added some extension through PDF, which requires Adobe Acrobat's distiller, but lets you plot things and use commands that is meant to be transparent, and then Acrobat will actually turn those on and create PDFs, and then from there tips and whatever that has transparency. So the top here is, typically what you will see if you plot a red rectangle on a map. Second one says, I want this rectangle to be 50% transparent. And rendering this with a distiller actually lets you do this. So that's cool. Automatic annotation selection, the -B option, if you know that, can now be automated. You can choose which kind of FFT algorithm you want to use. This is important for people who do a lot of processing that needs the fastest FFT on the platform they're working on. You have a real-time choice of which kind of triangulation algorithm you want to use for Delaunay and Voronoi triangulations. And then the 3D perspective view is now available in all programs. And we have a new enhanced macro language for designing your own symbols, which can be multi-variable symbols. So this little crazy symbol there has direction of the arrow, the angle of the arrow, and how many rings and their color. That's part of the data that you provide, and it will extend to 1, 2, or 3 rings, and it'll change the angle based on your data. So as many variables as you want. For developers, well, GMT5 has turned all the GMT4 programs that you are familiar with into a high-level API. There's a library that you can then use to write your own code. We also released this library under the GNU Lesser license, meaning that there's no issues with commercial entities wanting to use these libraries. So this broadens the potential use of GMT. And we're halfway through developing an interface to MATLAB and Octave that lets you get to all the GMT programs from MATLAB. And also, we can develop a Python API just after we finish the MATLAB API. So a lot of people are using Python these days, and they want to call GMT. They can do it as system calls, but it'll be slicker if you can call it as a function. You can store the variables and pass variables into the next function. So that's where we're headed. That means all GMT5 programs are simply a 10-line program. It looks like this. This is GRD image. It has 10 lines of code if you exclude the green comments, but really it's just 3 lines that is doing something. We create a GMT session. We call one or many GMT API functions. This one is GRD image, and we destroy the session. So this code behaves, that gives you the old GRD feel and functionality. And all the GMT programs look like this because all the actual stuff is hidden in the API, and you can get to the API with very simple calls. So the schedule for GMT5, as I mentioned, we did release a beta version in August. We did this for traditional reasons. Some people like to get a release and install it, and that's the time they install it. But it's a lot better to just get the latest from our Subversion repository, just stay up to date. Because since August, obviously, lots of bugs have been found and fixed. Why keep running that version? So better to go through our Subversion repository and install that. We had hoped to release GMT5 tomorrow on the 20th day, but we'd rather release something that works well than just hit a milestone on a certain date. So we're going to continue some more testing. We anticipate to release it maybe late 2011 or maybe just January 1st, 2012. That's the plan. I encourage you to visit our GMT5 website to learn more about this. We also have a new GMT logo contest where you can help design the next GMT logo. And the winner will win a GMT T-shirt with the logo on. So you can look like a real nerd. And that's all I had. Thank you for coming.